people have found that very useful, in particular those of you who are studying a course which has a timetable clash with this one. So functional programming then is not just about learning another programming language. For the most part, you can learn programming languages by yourselves. You don't need a lot of help. But I think functional programming is a little bit different. It's quite a bit more different than most of the programming languages you've studied before. And I think that you will benefit from this in a number of ways. You may turn out to be a big fan of functional programming, and this, of course, will be great to get you started on that route. It may be that you don't really like it that much at all, but I think whatever you do, it will make you a better programmer because it will give you a different way of thinking about programming. Now, functional programming is different because it's not based on the idea that is common in imperative and object-oriented languages, that there are these things out there with state, like bits of memory or objects that you change by sending them messages or applying commands, operations to them. Functional programming is very different in the sense that it is not built around that common theme. It's built around the simple concept of mathematical functions and values, and how we build values by applying functions, by composing functions, and so on. Now, functional programming is quite a broad term. We're going to learn about functional programming through one specific programming language, and that's Haskell. And the reason for that is that Haskell is, in some sense, the most functional of the functional programming languages. It's the most it's the programming language which is most uncompromising about its view on functional programming. Okay? Many other functional languages have other features which are not so functional, and Haskell is one of the few which can be considered to be purely functional. It's also a rather deep language. It's not a language that's necessarily that easy to pick up on your own. The concepts in it go quite a long way down. Even though programs seem very short and beautiful, there are of course lots of ways of doing them, of getting things wrong, and lots of ways of using the language badly. So I hope that we will not only learn about functional programming in general, but some of the very specific details of Haskell in particular. Question?
Is Haskell, there is more than one way to do it, language, or there is probably one way to do it?
Okay, so that sounds like a quote from a specific programming language that talks about only one way of doing things or many ways of doing things. Would that be a Perl quote or a Python quote?
Well, Perl would be the more than one way to do it, right? In Python.
Right. I don't think Haskell takes either of these standpoints as a design point. But I think it's fair to say there will be many ways of doing things, but if I say that, then you shouldn't think this has got anything to do with Perl or has any similarities to Perl. Okay. Very nice. Good demonstration. I obviously paid him in advance to show the rest of the class how you interrupt and ask questions. Very welcome. So you're all welcome to do that. I'm going to spend a lot of time sitting down here doing some programming stuff while you're watching. I might not notice questions if you just timidly put up your hand, so you may need to shout question to grab my attention, but feel free to do that. Questions are a good way to interact. It doesn't matter if your question's not too smart. They're good questions too. Just keep alert. If you ask questions about things which were asked 5 minutes earlier, then it's maybe not such a good sign. But questions are very welcome. Any other questions at this point? Okay, well, let me start then with actually showing you some Haskell. So let's see what we've got here. So let me open just a standard terminal window here. Okay, so Haskell doesn't have many implementations. So all of the implementations So the main implementation is the one you will probably be using for most of the time. and that is something called GHC. And GHC is actually a collection of things, one of which is an interpreter called GHCI. And GHCI is just a interactive interpreter, and you would have seen things like this before if you've played with languages like Python, for example, or maybe when you're developing hacking on JavaScript or similar things. So as an interpreter, it allows you to input bits of program, in particular expressions, so we can do some calculation with this thing in the obvious way. And that's all well and good, but actually we're not going to do a lot of our development of code within the interpreter. So what we're going to do, and what is usually done, is to develop the code in your favorite text editor. It doesn't really matter what it is too much. So fire up your favorite text editor and you can load code from there. So I'm going to do just that. I've got a file here, and I've called the file L01A, Lecture 1, Part A, or Lecture Week 1, Part A, .hs, so that's the name of the file down there. And so this is Emacs, if you're wondering which text editor this is. And Emacs is nice because it has a Haskell mode, so you'll notice that the stuff typed in here is coloured in various ways. I don't know how visible that is at the back, but hopefully it's reasonably visible. Okay, so what you would do if you were back in your terminal is I could load that file with a interpreter command, telling it to load, and I'll tell it to load that file, and it loads it, compiles it into some relatively simple form, checking the definitions as it goes along, and now it's loaded it, and you can now see in the command prompt that the file is there. So what else can you notice from this? Well, it started with something called Prelude, and now it's changed to L01A and some other stuff. Well, the other stuff includes the Prelude. So the Prelude is basically just a collection of definitions, a bunch of definitions of Haskell code that is loaded by default, and it contains a bunch of standard functions and other definitions. For example, it might contain some basic constants like pi, for example. So if I type pi, it gives me its double approximation. Okay, so that's what I can do in this file here. So I've begun this with a module name. This is not necessary, but it's possible. I could have left this line out altogether. You'll notice here some comments in a block, and the other kind of comments come on a single line. And then I've written some more comments that give me my plan for today. And actually this file contains at least one definition, and there it is. It's the definition of the exchange rate from euros to Swedish crowns. That's today's exchange rate. And so if we go back to our interpreter, which was over here, I can ask about the exchange rate, and it will tell me what it is. Okay, I'm not going to use this anymore, so I'm just going to stick to the one that's built into the editor here. Is that readable? Is that reasonably readable? Is that option? I can probably make the font a little bit bigger here. Possibly. Appearance. Yeah, that sounds good. Did that make it bigger? On the upper one, yeah, well I want the lower one. The upper one I think is big enough. Is the lower one readable? Is that good enough at the back? What do the guys at the back say? Yeah? Yeah, okay. It's a slightly different resolution than I was expecting here. Okay. All right, so we have a definition, and that was our exchange rate. I've just deleted it. Let's just get that back there. There it was. Okay, so let's define a couple of other things. So this is a definition. This is not a declaration of a variable. This is not something that a program will be able to change. So all definitions, things which are introduced with an equal sign, are immutable. They can't be changed. Okay, so this is a language that's built up from definitions of values and functions, and then we do computation by giving expressions which use the values and functions to compute new values. Okay, so we don't modify variables. All right, let's define a function. If I want to convert something to euros, I've got some number of Swedish crowns. I can define a function to convert Swedish crowns into euros. So what would be a good way of doing that? We take the Swedish crowns and we divide by the exchange rate. I think that would work. Okay, so there's a first definition of a function. Let me save it. Let me load it into the definition, which I can do, for example, by loading, which will reload it. Oh, sorry, let me reload it. That's what I wanted to do. I should have said reload. So my definition is fine. If I make some syntax error of some kind, let's put a bracket in there, you'll see that, of course, it doesn't accept it. It will give me a parse error of some sort or some other kind of error. Okay, and let me give just for completeness, I'll go the other way. If I have some number of euros, I can get the Swedish crowns by taking the euros and multiplying by the exchange rate. Okay. Now, the only thing you could notice about the definitions that I've given so far is that, maybe different from other languages you've seen, I didn't put in brackets around the argument to the function. Okay, and the reason for that will become clearer later, because in fact without brackets we can do more things with functions than with brackets, but for the moment you should just think of it as unnecessary syntax. Okay, so it knows that this is the name of the function, the space is then the space between the function and its arguments, and it has one argument. And so that's all the syntax that we need. The other thing you might notice is that we don't have any curly brackets. You may be very fond of your curly brackets. Curly brackets you use, I suppose, to tell you when something begins and when it ends. So this is a language with layout syntax. So the syntax that we'll be using here and in the textbooks will not use any curly brackets. But in fact, the language supports curly brackets. But we're using the layout style of syntax, so exactly the number of white spaces we use in definitions will be important. So it knows that this definition ends because there's a character starting in the same column position. So this definition ends at this letter T here. So that's the end of this definition, okay? Because it's in the same column. But otherwise, we could lay this out over several lines if we wanted to, and it will still compile. Okay? Any questions so far? All right, that's very good. I can now ask it to convert to euros my lunch, 80 crown lunch, and that would have cost me 9.21 euros. Very nice. Now, one of the things that we're going to push a little bit on in this course is testing, and in particular property-based testing, something which is well supported by some Haskell libraries. So towards that, what I'm going to do is introduce the ideas of introducing small bits of program which represent properties that we expect our definitions to satisfy. So what property might we expect our definitions here to satisfy? Well, we might expect that they are inverses of each other. That is to say, if I start out with some number of Swedish crowns and I convert those Swedish crowns to euros, and then I take the result of that and I convert that back to Swedish crowns, what we might expect is that that gives us the same as what we started with. So that's an example of, in this case, okay, it's not a very interesting test, but it is indeed a test. So let me just compile that, make sure I haven't made any syntax errors. So now I can test for these properties, my 50 crown example, and indeed it's true. It's true that if you convert 50 crowns to euros and back again, you get back to 50 crowns. Okay. Now, what are the purpose of these things? Well, you could think of them as the basis of doing a bunch of unit tests. We can define some things that we expect to be true. But actually, the way we're going to use it is a little bit more fun. We're going to use a library to do automatic testing for us, or rather to do random testing. Generate hundreds, perhaps thousands of random values and test the properties for us. In order to do that, I need to import the testing module that I have in mind.
Question.
Yep.
The property change, that's just a function that you there now. It's nothing special.
There's nothing special about it. The only thing that is so there is nothing special about it. This is just normal syntax that is allowed. You're allowed to use an underscore in a function definition, but this is a convention we will use, and that is generally used for this kind of property. So the fact that I call it prop underscore, I'm not obliged to call it that, but this is a convention we'll be using for properties, things we expect to be true of the definitions in our program. Okay? And the right-hand side here is something which is a truth-valued thing. In this case, it's a Boolean. So it either gives us true or false, but we expect it to always be true. And if it doesn't give us true, then there's something that's gone wrong. Okay? Okay, back up to the top. I've imported test.QuickCheck from the test sublibraries. I've imported this specific one called QuickCheck. Okay? Now, QuickCheck, it turns out, is actually written by my good colleagues John Hughes and Koen Klaassen. But QuickCheck itself, I'm not doing it just because it's invented here. I'm doing it because it's actually really cool, and you'll find it's also described in most of the textbooks. So this is a widely used library for developing Haskell code. Okay, so what can I do with it? Well, let me recompile that. Well, what it provides for me in particular is a nice little function called QuickCheck. I'll get the cases right. So QuickCheck. And what do you pass QuickCheck as an argument? Well, you pass it a property, something you expect to be true. So this is something called a higher order function. We're passing QuickCheck a function. And what is QuickCheck going to do with that? It's going to do random testing. It's going to throw, typically by default, 100 randomly chosen values, starting with small ones and getting big ones, to try and look for possible errors. Okay? So what happens when we do that? Well, it loads a bunch of stuff. And most importantly, down here, you see that QuickCheck failed. The test is false. It did 4 tests and 1 shrink. So after 4 randomly generated values, it found one which didn't work. This shrink is to do with the idea that QuickCheck uses of finding a counterexample, then if it can, finding smaller counterexamples. Because small counterexamples are much easier to understand in general than big ones. So it turns out the test fails. Anybody got any idea what went wrong? Yeah, it's to do with the precision. This is just standard rounding error. Okay? We're using floating point numbers. Here they're double precision floating point numbers, 16 bits. So we're getting the standard rounding error that we get because we can't represent these things precisely. There's nothing unusual about this, same as any other language. The point is that the equality test we're using is too strict. So we need something which is a bit fuzzier than strict equality. So let's define our own equality. Let's define when m is not exactly equal, but approximately equal to some other number n. So let's create a new definition. This time I'm defining an operator. What's an operator? It's just a function built from symbols rather than alphanumeric characters. And it's distinguished by the fact that you write it in an infix way. In other words, you write it between its arguments and not before its arguments. So what is it to be approximately equal? Well, we might say something like, I don't know, m minus n should be small. Some epsilon. What's epsilon? Well, I haven't defined it yet. Let me define it as a local definition. Just an excuse to show you a bit more Haskell. Epsilon is equal to, what's a good value for epsilon? So floating points, something like 16 decimal places. I reckon something like probably 10 to the minus 14 is probably the level of accuracy.
Here, if we are talking about euro and Swedish crowns, we don't need this precision, just -2 is enough.
Yeah, I guess so, if you want to, but I mean, yeah, so this is not important. So I'm also not doing any deep analysis of the level of precision of floating point representation. So, yeah, we can choose anything here, some small number. I'm making it rather extreme. It makes it look like we're doing really delicate scientific computations. Obviously, you're quite right. It doesn't make sense to be quite that accurate. But the point is, we will get that level of accuracy. We don't necessarily need it, but we'll get it for free. We don't have to do anything extra. The point is that the original test is wrong. So what I'm debugging here, I'm not debugging the program, I'm debugging the test case. Okay? That's not unusual. You get errors both in the program and in the code you use to test programs. And in this case, I'm debugging the test itself. So what I'm going to do is test whether these things are approximately equal. Okay. Okay, let's quick check that again. And we see that it passes 100 tests. And we can try that a few times if we want to. So it automatically. So is everything okay now? Yeah, good point. Good point. So yes, we found a test that it's true, but it doesn't necessarily mean that the test is in any sense perfect. It just is a test that is passed by our program. There are other bugs in the test. In particular, would you say that 3 is approximately equal to 5? I would say it isn't, but the test says it is. So what I'm missing here is to get the absolute value here. And there's a predefined function for that called abs, which will give us the absolute value. Okay. Any questions? All right, just for the sake of completeness, how would we have actually defined abs if it wasn't available to us? The absolute value of some number, well, we could use a conditional expression. So this is the most familiar way to you. If m is less than 0, then the answer should be minus m, otherwise it's m. Okay? So that would be a reasonable definition of abs. I can't redefine it that way because I'll get a name clash. But if I was to define it another way, there's a language where there's more than one way of doing things. Let me define it called abs prime. So I don't have a name clash with the one that's defined in the Prelude. Another way of defining this is to use guards. So the syntax for this is to say that abs prime of x, in the case that x is less than 0, should be minus x. And abs prime of x, in the case that x is greater than or equal to 0, will just be x itself. So here's an alternative definition. So it's a definition that uses more than one equation, but each equation has a guard which tells me under which conditions I should use this equation. And equations are used in strict order, so the system will look for an equation which matches, and if it doesn't match, it will go on to the next equation in a series of equation definitions.
So we just need the first line.
We could just have the first line, so let me just comment out the second line. I can compile that, and I can apply abs prime to -2, and I get 2, so it does work, but if I try and apply it to a positive number, I get an error. I get an error because I haven't got a definition for what the function should do when x is not less than 0. Yeah?
But we can put abs prime x equal x.
We could do that, yeah, we could do that, but let me just show you stylistically how it would typically be done. So firstly, to note, when you have two equations which have a repeated left-hand side, then the standard style is to eliminate, is to remove that bit of here. And I'm putting white space in just for readability, so it's not crucial to the definition. Okay, so that's the first point. The first point is now we get a definition of a function by two cases. So this is actually looking quite like fairly standard mathematical notation when you define functions by cases. Okay. The second thing we can note is that the second guard, if the first guard is false, the second guard will always be true. Right? So why do we bother testing it? We know that will be true if we ever get to this line. Okay? So we could actually replace this by the value true, because a guard in one of these expressions is any Boolean valued expression. Stylistically, you don't do this in a Haskell program, not because you can't, not because it's wrong, just because this is not the typical style that you would use. You would actually use something called otherwise. So a typical way you would see this defined would be like this, lining them up nicely just for readability. It would say that abs of x, when x is less than 0, is minus x, otherwise it's x. Okay? So then the question you might ask yourself is otherwise a keyword in Haskell?
Or is it defined to true?
He's on the ball. Other words, it doesn't need to be a keyword. It's just something defined in the prelude to be true. I can actually ask the interpreter, give me information about otherwise. And it says it's a Boolean valued expression and it's defined in some sublibrary that is imported by the prelude. And if you want to actually see what otherwise does, it is actually true. Okay? It just gives a more readable a mathematical style of definition.
So you can never define the variable true in the program, because it's always different.
True is not a variable.
Or
True is a value. So what you notice about true is that it starts with a capital letter. I can't define constants or functions that begin with a capital letter. So it's case sensitive. So I can define true equals false, but I can't do this because it would be a syntax error. And you can actually see that the Emacs mode here, that my editor knows about this rule and actually colors this in green and this one in blue for those of you who are colorblind or struggling to see the colors. I don't know why I wrote that. That's a terrible thing to write. Okay, any questions? All right, very good. Okay, so now second topic I want to move on to here. We've seen a little bit about basic functions, not doing anything very interesting. One of the ways that we can do something a little bit more interesting without much more machinery is to build recursive definitions. So everybody here knows about recursion. You've all seen recursion, right? Okay. Well, if you haven't, write an angry letter to your first programming teachers because you should have seen recursion. You'll get the hang of it as we go along. So let me give you an example of programming with recursion using the function power, which corresponds to the exponentiation operation. So if you have 2 to the power 4, that gives you 16. So I'm going to define my own version of this and not use the built-in one. And this is a function which is going to take two arguments. The first argument, let's call it n, and the second, which is k. So we'll do 2 to the power 4 will be power 2, 4. And this will be a version of the power function that assumes we have a natural number or a positive integer exponent, a non-negative integer exponent, natural number exponent. Okay. So I'm going to give a definition for this, and I'm going to do it by cases. And the first case is when k is equal to 0. And then what should the answer be? N to the power 0 is 1. And in the other case, well, which case is it? It's when k is greater than 0. So now we're going to use the power of recursion. And the idea in recursion is to try and solve a bigger problem in terms of the solution to a smaller problem. Okay? Now, what smaller problem it is depends exactly on the nature of the problem you're trying to solve. But the natural case, if I'm going to define a very simple and naive recursive power function, not a very smart one, I'm going to try and define what this is in terms of ... the function power of n and k minus 1. So let's suppose I know how to compute n to the power k minus 1. How would I get n to the power k? What would I do with this to get n to the power k? You'd multiply it by n. One more copy of n. And there is my definition of the power function. Any observations about that power function? What happens when k is negative? Well, yeah, we know that there is a negative, but I've decided I'm going to have a power function that only works for natural numbers. Okay? So that's fine, but actually there is a good point there. Even if I only want it to work on natural numbers, it can be rather useful to at least let the programmer know when things go wrong with a sensible error message. So if I want a sensible error message, I want to say if it's not one of those cases, what should it be equal to? Well, it should be an error, it should crash, but I want to give a more sensible message. I can do that by using a function called error, which all its job is to crash, but crash with a message of your choice rather than the choice of the runtime system. So now it gives me an error message, which is a little bit more sensible. So if I want power on minus, I get my error message. Otherwise, I get something fairly sensible. Any questions about that? Okay, let's just tidy this up a bit. Remember what I said before, is that whenever we have repeated left-hand sides, we can actually leave them out. So we could write that. We could also eliminate this, but actually there's another bit of syntax that I can introduce to you, and that's the concept of pattern matching. Here we have a guard which is testing for equality with a value, and actually it would be more normal here to put this into the definition itself and say directly, power of n with exponent 0 is equal to 1, power of k when k is greater than 0, and so on. So that might be a more standard way of writing this. So this is the first time we've seen this. We're using a value on the left-hand side. This is called pattern matching. Any questions about that?
Yes.
Yeah.
So this is an exception. So that's
Yes.
So if you have an exception somewhere repeating your function, will it just jump out of that function, or will it run back and we can run calculations?
Yeah, basically for the purpose of this course, exceptions are basically just runtime errors. Now there are certain circumstances in which you can catch exceptions, but not in the part of the language that we're considering here. So you shouldn't think of these exceptions in the Java sense of catchable. You could just think of these as uncatchable exceptions. So these are causing any program to immediately terminate with an error message. So we shouldn't be encountering these in normal use of our definitions. Any other questions? Okay. Let me just jump into my slides here because I want to talk about. So I have lots of slides, but I'm not using them because I prefer to do stuff live. But if you want to pretend, you can. Okay, so let me just leave before we take a break. Let me leave you with a little puzzle to think about. The way that recursion works is just a reminder: is that you take a big problem and you reduce it to a smaller problem. The reason why it works is because you have something that will stop you going on forever. There will be a base case, something that will, in some smallest problem instance, which you immediately know how to solve. In the case of the power function, it was the case when the exponent was 0, we know that the answer is 1. And for all other sensible cases, we reduce the problem of solving the bigger problem into one of combining what we know with the solution to the slightly smaller problem. Using this way of thinking, during the break, I'd like you to think about this little problem. It's the problem of counting the number of intersections, the maximum number of intersections you can have with n distinct non-parallel lines. So here we have a picture with 4 parallel lines. And we have 1, 2, 3, 4, 5, 6 intersection points. So when n is 4, the answer is 6. That's the highest number of intersection lines that we can get. So I'd like you to think about how to define a function that computes for any n the maximum number of such intersections for n lines on a plane. Any questions before we take a break? Okay, we'll resume again at 1:15.